So this is problem 2.11 from Modern Physics by Kenneth Krane. And this one is another velocity addition problem, but a little bit different. So rocket A, we'll call that this, leaves a space station at a speed of 0.826 c. Later rocket B, which we'll call this, leaves in the same direction with a speed of 0.635. What is the velocity of A as observed from B? So obviously velocity addition, I'm going to use this equation. Just like before. So what do we know? Well, our reference frame will be as somebody, I don't know why his head's sticking out in space, that's not very good, but from somebody on ship B. Now its reference frame is given, that's U. U is the reference frame, which is this, so that's good. Okay, so that's that part. We also know that the speed that the other ship is going with respect from the space station is 0.826 c. That's your v, not your v prime, your v. That is the speed that a stationary observer measures. So the only difference with this problem is we need to solve for v prime. That's the speed as observed from rocket B. So this is just a little bit of algebra. Multiply both sides by the denominator. Honestly, if you're okay with that conceptually, that's probably the hardest part. This is just the algebra. I just think this is, U is your reference frame. That's how they use it in the book. And then just know that V is the speed as measured from the space station, you could say. You can distribute. I'll go ahead and work through the algebra in case that is a problem. Again, we're looking for V prime. So I'm going to I am going to subtract over this V prime. I'm going to subtract over this V, just to get V prime on one side. And now I can factor out AV prime. Like this. Now I can divide all this over to find V prime. So U minus V divided by VU over C squared minus 1. And again, we know U and we know V, so all we need to do is plug this into our calculator. And when you plug this in, you get 0.402 C. Okay? So that is the speed of ship A as measured from ship B. Hopefully that makes sense for everybody. Conceptually, does it make sense? Yes. Number one, it's below the speed of light, which is good. Anything over the speed of light, that doesn't make sense. And it also makes sense that the speed is less from the perspective of ship B than it is from, say, some space station over here. I don't know. I'll just draw. I don't know what a space station will look like. Let's just say it's this. That's because they're both moving. So if you think of this as two cars, one going, let's say, 80 miles an hour and the other going 50, from the perspective of car B, you're only going 30 miles an hour. Obviously, from a stationary point of view, it's 80. But the point being, ship B is going to see a smaller velocity, which is what we get than a stationary observer would. So conceptually, that makes sense as well. So if that helped at all, please subscribe and maybe even like the video. It helps me out. So if you could do that, that would be great.